we're going to work one more problem that using the Bode plot approximation for the frequency response. And we're going to look at a system that has 1, 0, and 2 poles. So if we have a system of one pole, s plus 1, 0, 0 at -1, and then we have s plus 0.1 and s plus 10. So we have 2 poles. What does this look like if we take the frequency response of it? Okay, so we are going to do, the way I like to start a problem is to look at first what the system looks like at very small values of s. So if s equals 0 or approaches, I guess goes towards 0, in this case we see that if we take g of s equals 0, we're going to get just 1 divided by 0.1 times 10, which is just equal to 1. So if we take the magnitude of that, that's going to be log 10 of 1 is 0, so we have 0. And if we look at the angle of that, so phi of g here is going to be, well, 1 is positive on the real axis, so we're going to have 0 degrees. So at very small values, we know that this system is going to look like a 0, this is 0 dB, and 0 degrees. So we can start by just drawing that out here. So here we have 0 dB, we start here. Here we have 0 degrees, we start here. Okay? And then at the end, as s goes to infinity, I guess there should just be one line there. As this goes to infinity, what does it look like? Well, as s gets very large, the s's are the only thing that matter. So we'll have, these two will effectively cancel each other out, 1, 0, and 1 pole, and we'll have just 1 pole left. So it'll look like 1 over s. If we look at the magnitude of that, well, we don't know the exact value, but we know that it's actually decreasing at 20 dB per decade. And then if we look at the angle, we do know the angle of 1 over s. So g of infinity approximately will look like 1 over s, right? And so if we know the angle of that is going to be -90. So g is equal to -90 degrees here. So that's as we go to infinity. So we don't know exactly what will happen. We'll know we end up about at 90. You can see my graph here from 90. And we'll be decreasing. We don't know exactly where yet, so I won't draw the line here. Okay, so now let's look at what happens as we go through where these poles are located. So the first one, the lowest value one, is 0.1. So I'm going to try to use some creative darts here. So the first one is 0.1. So we have the pole effect here. And that will start changing the magnitude once the magnitude crosses that threshold of this value. Now this is the approximation, right? So we know it will start to affect it before we get to this point, but we approximate it as a straight line until then. Once it hits this point, right, this first pole, it'll start to decrease at -20 dB per decade, because that's the effect of the single pole. So it'll decrease at 20 dB per decade. So here's our next decade. -20, go to this point. Okay? And the effect of the phase is plus or minus 1 decade. So the effect of this one pole is actually going to affect the phase, hope you can see this, from 0.1 to 1. And it will affect the phase by making it try to decrease by -45 degrees per decade. So we can start drawing that one. So we'll draw up to here. So we are going to see it decrease by -45 degrees per decade. So we'll get approximately to 45 right here per decade. Okay. But now we have the effect of the next pole. So, or sorry, 0. So the next one is 1. So here we have 1. And in the magnitude, we know it's going to do the opposite of the pole. It's going to make the magnitude increase by 20 dB per decade. So we have the effect of this 0, which is making it decrease by 20, This one is being increased by 20. So net, we have 0. So what happens between here and our next bolt, which we know is 10, is we're actually just going to see a approximate stability, so staying at 1 magnitude until we hit the next pole. So these two cancel each other out, and that's what we're seeing in between these 2 points, so between 1 and 10. Okay? Let's look at the phase, how that affects the phase. So here again we have 1. So the effect of this 0 will affect positive and negative 1 decade again. So once we hit the 0.1, we are getting the effect of this 0. So between here and here, we're decreasing by 45 degrees per decade. And between here, we're increasing by 45 degrees per decade. So really we're, again, neutralizing. So we're actually just staying approximately at 45 until we hit the end of this effect. Okay? Okay, so if you're with me so far, things are looking good. Okay, so now we're going to move on to the last pole here. So that's at 10. So we've hit this point. I don't have enough darts, so we have to reuse darts. So here's our dart for the pole here. And now we're going to see the effect of this pole being added onto what was on here. So these two cancel each other out. Negative 20 dB per decade, positive 20 dB per decade. And this last one is going to contribute another negative 20 dB per decade. So that's what we're going to see from this point on. So we're going to decrease here, and we just continue to decrease at negative 20 dB per decade. dB per decade. And this one I should have labeled as well, was negative 20 dB per decade. Okay, so this is the full magnitude plot, our approximation. So we see the effect of first the pole, then this 0, and then this pole. And then as we go on to infinity, we just see the effect of this, of 1 pole. Okay, so that's that. Now let's look at the phase one more time. So we've gotten up to this point on the phase. Now this pole no longer affects us after here, but we have the effect of this pole. So this pole, turns out they overlap, affects 1 plus and minus 1 decade, right? So at 1, we're going to start seeing the effect of this pole. We already have the effect of this 0, right? So here again, in between these 2 points, we're actually going to, the two effects will cancel out. So one will want to increase by 45 per decade, one will want to decrease. Again, we get 0. So we get 0 up to this point. And then we reach the end of this, the influence of this pole. And now between here and here, we just get the effect of this final pole at 10. So we'll get a negative 45 degrees per decade. So here's that here. And I recommend labeling these in case you're not as good of a drawer as I am. It's good to label them so that people know what the rate they are. And then this one we end at, and just to clarify, this would be negative 90. So the addition of all these rates of angles should be the same, but we also already calculated that we need to end at 90, so we know our ending point here. Okay? And just to double check, we ended with a negative 20 dB per decade, which is what we expected as we go to infinity. Okay, so we looked at the effects of the 2 zeros in the pole and the magnitude of our frequency response, and how it influences approximately the phase. Okay, so that's how we would approximate the frequency response for a function like this. Now we can look at the same problem in MATLAB, and we're just going to set that up and say g is equal to transfer function, and our numerator is 1 and 1, and our denominator is, if we multiply it out, 1, 10.1, and 1. So we can check that it looks correct, looks great. And now we can simply do the Bode plot of G, and we should see the correct Bode plot. Sometimes MATLAB takes a little while. There it goes. Okay, so now you can see that we don't get the exact approximation, right? But we do get starting at a constant value of dB0, which is 1, and then we see the effect of the first pole, then the effect of the 0, so you can kind of see it here as well, and then the effect of the second pole, and then as we go to infinity, we are decreasing at, should be 20 dB per decade, and you can see that as well. So the lines that we drew before give us an approximation. If you want to see the actual calculations, you can do it in MATLAB or calculate all the points, but the approximations give us a pretty good picture without doing a lot of calculation. So that's this example shown in our Buddy plot in MATLAB, and I hope you now know how to approximate any basic transfer function.